In this next section, 28.3, we're talking about the formation of the solar system in terms of the standard gravitational model. And because of that model, it's actually been around since Isaac Newton's time. We're going to look at part one of 3 parts, which is called the LaPlace Solar Nebula Theory, or the Solar Nebula Theory. We've already studied nebulas in prior sections. This one's a little bit different, has a different wrinkle in terms of predicting what the solar system and how it formed. It's been a long-running debate as to how it formed, and by solar system, we're talking about our sun, Sol, and all the bodies revolving around it. You can see from this video depiction, we usually have a nice little picture of the sun in the middle and all these little rings around it where the planets are sitting in it, for the most part, in a nice orbital plane, with Pluto being the only goofball that kind of is out of the plane. And as you see, the sun is actually moving around the galactic plane, the Milky Way galaxy, in one of the arms. And so as it's moving, all the planets that are in its gravitational pull are trying to keep up. So the actual motion is more the spiral or corkscrew effect. So the planets are not only trying to keep up in this corkscrew effect, even the moons around the planets are trying to do the same thing around them. So it is not a simple process. But we're talking about this one as far as when it was formed. It was in the 1600s to 1700s. It was believed the sun formed first, and that it was actually a hot molten ball, almost like lava, because that's all the people knew at those times. Lava was hot and kind of that reddish glow, and that the material, as the sun rotated, was flung out from the sun, where it cooled down, much like lava does here, to form the rocky bodies. And it wasn't until 1796, almost the end of that century, rolling into the next one, that a mathematician, Marquis Pierre Simon de LaPlace, he theorized that the sun and the orbiting bodies all came from the same nebula at essentially the same time. And at this point, we had telescopes, and that they were seeing the nebula gases out there. So it was a natural extension from those studies that he knew that it was plausible. And it became the accepted theory eventually, and we call it the LaPlace Nebula Theory. So he's saying basically, as this whole nebula was cooling down, the center was condensing and creating a hot ball, which is the star, and that in concentric rings, as materials would collide and coalesce, form bodies, kind of cleaning up the debris of the dust particles. And according again to this current theory, the Big Bang spread the initial matter throughout the expanding universe, which we talked about when we studied universes. And some would gather in these nebular clouds and dust particles that eventually developed into our solar system. And the initial cloud material is called the solar nebula. So we studied the light and dark nebulas. This one's a little bit more dense, hence creating a solar system. So from the Big Bang throwing out all its materials as they coalesced, became this body of gases that became much more concentrated, where the center would then collapse into the star, and these would separate into bands, creating planets, according to this theory. And it also had the problem is that gravity is a weak force. Of the 4 forces in nature, gravity is one of those 4. It is a weak force compared to the other ones. There's 2 weak forces, 2 strong forces, and it's very, very weak. And so they realized soon afterwards that they had a problem, that gravity couldn't pull these things, especially gases together. Gases tend to expand to fill the container they're in, and if you're in the vacuum of space, they're not coalescing. So what they then added to this theory, and they modified it, there's an external force of immense energy, most likely a nearby supernova strength, where it would create a bow shock and force these gases and these particles together. As you get them close together, they start to rotate, much like an ice skater pulls their arms in, they rotate faster. That's called angular momentum. And when you have that, the materials then will collide much greater frequency, and not only that, generate heat for fusing and melting together. So our sun, a main sequence star, which we've also studied in the Unit 1, was formed through such collisions and angular momentum increase in pressures. Again, we saw there. Our solar nebula itself, about 99% of our finished galaxy, if you will, about 99% of the mass in this nebula is in the sun, 99 plus. Everything else around it is a little bit less than 1% in those orbiting bodies. So it shows you how much was drawn out of their cloud based on the model, where it went thermonuclear and started creating these rings where the materials within those rings, much like Saturn's rings, started to coalesce into rocky bodies. So the sun's 99+% of the mass of our nebular cloud, and everything else is a little less than 1%. And while the sun was forming at the center of the solar nebula, the planets themselves were forming in the outer regions. So this little animation GIF kind of shows as the going planets starting to pop into existence, orbiting the sun in the early days, according to the Solar Nebula Theory by LaPlace. And that's it for this section.